Today I'm going to go over the Chapter 5 Comprehension Check. So for question 10, we're going to be drawing a compound and we're going to be deciding its shape. And so before we get into this, you need to understand something called the VSEPR theory. VSEPR stands for valence shell electron pair repulsion. And what that is telling me is if I have lone pairs of electrons, they're going to repel each other. Two sets of negative charges are going to push apart. So as we draw these, this theory tells us that these electrons are going to try to get as far apart away from each other as possible because they have some repulsion between each other. Now this gets a little complicated because we're talking about 3D shapes that your book has smushed into a flat page. And so if you have some toothpicks and some clay, I would encourage you to get out some sets and try to make some of these, and it may actually help you to visualize the 3D shape instead of just trying to look at it as like smushed onto a 2D board. But question 10, I'm given a molecule and I'm asked to draw like the stick figure for it and determine its shape. The first thing I have to do before I do this is draw the Lewis structure for this. So we've talked about carbon and we're gonna put carbon in the middle. And I'm just going to be using dots for my electrons because carbon is 4 electrons. Now I have my hydrogens. If you want to go ahead and put your hydrogens around, it doesn't really matter where. In each hydrogen, I've got 2, and each one has 1 valence electron. Oh, and it's a Cl too, I forgot that. And then I also have 2 chlorines that I'm going to put on here, and each chlorine we know has 7 electrons, 7. So each of these 2 chlorines have 7 valence electrons. So within your hydrogen, these two, this hydrogen-carbon bond makes a bond, and the same happens up here. And you get a carbon-chlorine bond between the carbon and the chlorine. And so this is what your Lewis structure is going to look like. It does not matter if you put the chlorines on each side or the hydrogens on each side. Now the question is, what shape does this make? And so if you'll look back in the reading, when you have something in the middle that can make 4 bonds, we actually call that shape a tetrahedral. It's the same prefix for 4. And so it means 4 things are coming out of this shape. It's really hard to take a tetrahedral that is 3-dimensional and stick it on a board. But if I was to make it in 3D, it would look like this. So the 2 on the top are hydrogens, and we're gonna use chlorine is gonna be these 2 greens. So the reason I say it doesn't matter how you orient it when you draw it is I could hold this tetrahedral this way and 2 hydrogens are on the side, the chlorines are on the top, but I could also hold it this way and you see the hydrogens next to each other if you made this look 2-dimensional, and the chlorines next to each other. They're both fine. But when we draw a tetrahedral in what we call a stick figure shape, you're gonna draw it and it's gonna look a little bit weird. So you're gonna put the carbon in the middle, and I'm gonna draw just a straight stick up towards my hydrogen, and that represents this hydrogen that is in the same plane as the carbon, okay? And now I'm gonna draw, if you'll look also, I have another, if I hold it this way, I'll try to hold it the same way I'm gonna draw it. I have another hydrogen that's in the same plane as the carbon. So if you'll see, these 3 atoms are like in the same plane, I hope that makes sense, of each other. And so I'm gonna use a stick to draw that hydrogen. Now, I have 1 chlorine that is coming like out towards the screen, and I have 1 chlorine that's going back. And so for the chlorine that's going kind of back, you're gonna see in your book this little hash mark. So this is the chlorine that's like going through the board. And the chlorine, oh, I wrote hydrogen. And the chlorine that's coming out of the board gets a wedge. I hope that makes kind of sense. If it's within the plane of the board, we just use a line. If it's going behind the board, you have that like hash line. And then we use a wedge if it's coming out. And so this shape we call a tetrahedral. There are several of these shapes. There's bent, there's tetrahedral, there's pyramidal. You're going to have to just memorize them. Question 11 is asking you for the shape of carbon monoxide. So we already drew this once, I think, but we're going to do it again. So carbon has 4 valence electrons and oxygen has 6. Now, if you remember the way that I drew this earlier, this carbon and this oxygen makes a bond. This carbon and this oxygen makes a bond. This is just like what we call a lone pair of electrons. Now, if we leave it like this, technically carbon has 1, 2, 3, 4, 5, 6 electrons, so it's not satisfied. So one of these is going to move over here and make a triple bond. We talked about this in one of the other on your own questions. So the question is, what shape is this? Anytime you have a 2 atom, it's just going to be linear. These are going to be 2 atoms that come right in a row. Now, since electrons repel, these electrons will push out to the side, and you're going to have a linear shaped atom. For 12, we're going to do the same thing. We're going to draw SF2. We are going to start with the Lewis structure of this. So I have a sulfur in the middle, and it has 6 valence electrons. You don't have to draw them that way necessarily. You could put the 2 near each other. And then I've got 2 fluorines, and fluorine, as we know, has 7. These electrons are going to come together to make a bond. Now, technically, the way I've drawn this is incorrect if I'm going to draw the stick figure. So if this would be your Lewis structure, it's fine. But if I'm trying to show this shape, so what the valence shell electron theory tells me is I've got these 2 big valence electrons out here, and they are pushing apart from each other. And so I have a single atom, and I have four things coming off of it, right? If you say 2 fluorines and 2 electrons, and these electrons are going to be pushing away. So I'm trying to make it. So these electrons are up here. One technically would be coming back into the board, and one would be coming out of the board, and they're taking up a lot of space, and they're pushing, these are the fluorines, down, and this is the sulfur. So the shape that this makes, as I've drawn it incorrectly for my Lewis structure, but it makes, when we make this stick structure, it's called a bent shape. So this would be the stick structure, and these are all within the plane of the board, so I'm just using a line. And the reason that we get this shape instead of this one, I mean, technically, if you were to take this shape, like it's 3D, and I rotated it this way, right, it looks like my shape on the board. So we draw it this way. This happens when you have 4 things off the central atom, but 2 of them are valence electrons. And you're just gonna have to kind of start to learn these rules. The last one that we had, where we had 4 things coming off, but they weren't valence electrons, we called that tetrahedral, but this is a bent. So question 13 gives me ammonia, which is NH3, and it asks, is it polar or is it nonpolar? We haven't talked about polar and nonpolar in terms of a molecule yet. So a polar molecule is a molecule that has an imbalance of electrons, and a nonpolar molecule is a molecule that has an equally balanced electrons. We cannot figure this out unless we draw its Lewis structure. So we have nitrogen, which has 5 valence electrons. And then I have 3 hydrogens. And this hydrogen-nitrogen is going to make a bond between each one of these. Just like that. And on page 144, your book does a really good job of explaining this. So even though this nitrogen's in the middle, has 4 things coming off of it. We've talked about when you have a central compound and it has 4 items coming off of it. If it has 4 atoms, it could become that tetrahedral shape. If it had 2 atoms and 2 electrons, it made the bent shape. But this has 1 pair of valence electrons. And valence electrons are actually pretty big. They take up a lot of space. So this one has a pair of electrons on the top. And what happens is those valence electrons, because of that valence shell electron pair repulsion theory, is those electrons on top are pushing these down. And you get this really funny pyramidal shape is what this guy is called. Since it's a pyramidal shape, you have nitrogen. There's 1 hydrogen in plane of the board, 1 hydrogen going behind it, and 1 coming out. And then you have all these valence electrons up at the top that are taking up a lot of space. So the question is Is it polar or nonpolar? We have some strong electrons up here. And so this is a strong negative charge to the top of this molecule. And so this is a polar molecule. It doesn't have an even balance of charges all around it. Question 14 gives me another compound. I'm going to draw it. It wants you to tell, is it polar or nonpolar? So we have one silicone, which has 4 valence electrons, and we have 4 fluorines coming off of it. Now, there are 7 valence electrons on each fluorine. I really don't want to draw all of those right now. So we're just going to draw the bond like that. I realize I got a little lazy on that. What this is when you have one central atom and you have 4 atoms coming off of it, you get that tetrahedral shape. So we get 1 fluorine on the top is in the plane of the board, 1 is coming out in the plane of the board, 1 goes behind it, and 1 comes in front of it. It would look like this. So we have 1 coming above it, 1 in the plane of the board, 1 coming in front of the board, and 1 coming behind the board. Each of these fluorines are evenly spaced apart. They're pushing at the same distance from each other, and they all have valence electrons on it. So for this compound, I don't have a bunch of extra electrons on one side. They're all around this compound. So this is a nonpolar, which means one side does not have a stronger charge. Comprehension check 15 refers back to question 13 and 14. So in 13, we drew ammonia or NH3, and we came up with that it is polar because it has all those electrons on one end. And in 14, we did silicon tetrafluoride, and it is nonpolar because it does not have those valence electrons that are pulling unevenly. And so the question is asking which one will dissolve in water, which one will dissolve in oil. To know which one will dissolve in water, which one dissolve in oil, I'm going to show you a water molecule. Water is H2O. So I have 2 hydrogens and 1 oxygen. Now, the oxygen has valence electrons that are coming off the top of this shape. So envision there's valence electrons up here. These valence electrons have a large push, and they push these hydrogens down, which is why you get water in this bent shape. But because water has all these electrons on top, there's 4 or 2 pairs, it is a polar molecule, which means it has one part of the water that is a negative charge and one part that is more positive charge. Now, when we are talking about what dissolves in what, the rule is like dissolves in likes. So polar compounds dissolve in polar compounds, non-polar compounds dissolve in non-polar compounds. So the question is, which will dissolve in water? Well, this is polar, so it will dissolve in water because water is a polar compound. And this is non-polar, so it will dissolve in oil because oils or fats are non-polar compounds. All right, I will see you for the next video of the Chapter 5 review questions.